Hi there. Welcome to CMU's Career and Professional Development Talent Insider. Today we're going to be hearing from Dr. Jillian Ryan, our Associate Teaching Professor and Director of Undergraduate Affairs of our Physics Department. So Dr. Ryan, I will hand it over to you, and we're looking forward to hearing more about our Physics Department here at CMU.
Wonderful. Thank you, Heather.
Sure.
So in my role in the department, I work very closely with our students, both in terms of academic and professional advising and overseeing the curriculum in the department. And so my goal today is really to convince you that our students are people that you want to consider when you're seeking new talent for your workforce or for your organization. And I want to kind of start by asking a question and then answering it, because it's one of the questions that I hear commonly, both from incoming students, from current students, and from our partners in various organizations. And that's whether or not a physics degree prepares students to enter the workforce. I think a lot of students that are considering their options coming into CMU ask this question. I know their family members do. And I know that our partners are concerned or wondering what a physicist may be able to do if they were to hire them into their organization. And so I'm going to start hopefully by reassuring you that physicists absolutely are prepared to enter the workforce. And that is not coming just from me. This is also coming from the American Institute of Physics. So the AIP is the national sort of parent organization of many of our professional societies here in the US. And they annually provide surveys where they essentially survey departments across the country about the number of graduates and their placement after graduation. And so we typically have around 40 undergraduates every year that graduate with a degree in physics. And I can tell you a little bit anecdotally about our students in a moment, but I want to show you some larger number statistics. So there are thousands of students that graduate every year in the US with a degree in physics, and a large number of them enter the workforce directly. So here, national statistics on the left, you can see by year. And in orange, you can see the students, the number or the percentage of students that are employed directly upon graduation. And this obviously varies a little bit over time, but we typically see that this is in the high 40%, close to 50%. So that means that roughly 50% of our students are directly entering the workforce with an undergraduate degree in physics. The vast majority of other students that don't do this are going on for continuing studies, either in graduate degrees or professional programs. But we are seeing a very large number of students directly entering the workforce. And on the right-hand side here, you can see the most recent data. So there's a bit of a lag in the data reporting from the AIP, but data from 2019, 2020, we saw about 46% of undergraduates had a placement in the industry or were employed immediately upon graduation. Now, where are they going? I think that's an important question. On the left-hand side, you can see a pie chart. And this is showing the different sort of areas of employment. And so we see that the vast majority of our students nationally are going into the private sector. Approximately 60% go into the private sector. There's some number close to 18% that go to work at colleges or universities, either as research associates or technicians or in other roles. A number of them go to work to teach high school, so about 6%. Some directly go into the military, and around 7% go and work in government labs, either national labs or at the state level doing work there. And so I want to specifically talk about the private sector and the type of roles that our students are capable of fulfilling in the private sector. Now, on the right-hand side here, we have the pie chart of those private sector employment opportunities. And so these are students that graduated in 2019, 2020 across the US that entered the private sector of employment directly after graduation. And I want to kind of point out that very few of these sectors that we're looking at say physics. Physicists are very versatile. They're capable of succeeding in a wide range of environments, and they have a lot that they can bring to a workplace. And we see that roughly a third of our graduates nationally go into an engineering field. So they're working somewhere, either in an engineering organization or group, or in a role that is considered more engineering than physics. We see roughly a quarter are working in computer software. We have a large number of students who work as software developers or as computer programmers. So taking those analytic skills that they've developed as an undergraduate in physics and applying them to computational programs. A small fraction, around 14%, work in non-STEM areas, but they are using their problem-solving skills or their technical skills to solve problems. Again, quote, 8% are in non-STEM that they say they rarely use technical problem-solving skills or solve technical problems. Around 15% are in other STEM areas, and the smallest wedge here is the one that specifically says physics or astronomy. So we do have students that go into roles where physics is, for example, in the job title or a very clear part of their role. But the vast majority of students that graduate with an undergraduate degree in the US in physics are not working in a position where physics is in their job title. And I want to kind of emphasize that this means that when they're seeking employment, and sometimes when employers are seeking employees, there can be a mismatch where physics students can be overlooked. And so I'm hoping today to convince you that you may want to more directly seek out physics majors when you're seeking to hire in your organization. Now, we have a good success of placement of our students upon graduation. We follow here at Carnegie Mellon the national trend that roughly half of our students go on to graduate studies or professional studies upon graduation, but the other half directly enter the workforce. And I want to emphasize again that their titles don't necessarily say physicist. So I took some job titles from graduates from the last couple of years, and we see that they're getting hired as chemists, as lab technicians, as engineers, as software developers, as analysts. And we see that there's a very diverse subset of organizations and work titles that they're being hired into. I think there's maybe 2 titles here that have physics in the label. The optical physics chemist, and then of course the associate physics engineer. The vast majority, I think if they were kind of looking at the ads, our students were working on training them to really look at advertisements to identify the skills that are being sought, to identify whether or not a position would be appropriate for them, because often something like a software developer or an engineering technician requires the same skill set that our students have. And so we're working on our end to empower the students to reach out when they see an ad. But I also want to highlight to those who might be writing ads to consider physics as an appropriate background for these positions. Now, when our students go into the workplace, I said the 2 biggest sectors nationally were in engineering firms and in some form of computation. Now, we see this reflected here in our students as well. So we follow the national trend fairly closely. You can see a number of titles here that say engineer or, for example, software engineer or software developer. And again, the American Institute of Physics really does due diligence in terms of tracking what students are doing upon graduation. And so they surveyed students who directly entered the workforce in 2019 and 2020. So these are students that have now been in the workforce for maybe 2 or 3 years. And they specifically targeted students who had identified engineering or computational or computer science fields as their areas of employment. Now, they surveyed them and they asked them, well, what skills do you use on a daily basis? And they identified things like working on a team or solving technical problems, all the way through managing people and managing budgets. And I want to point out the colors here. So engineering is shown in blue on the left. The dark blue indicates that that is a daily task. So that's a skill they use essentially daily or weekly, whereas the lighter blue indicates skills that they use maybe monthly. And so we can see, for example, that a large skill that students or graduates that have identified as being helpful that they use is working on a team. They solve a large number of technical problems, mostly on a daily basis. Technical writing, most use daily or monthly, design and development, quality control, and so on. Now, very few of these skills require very specific physics knowledge. However, a physics education prepares a student for using these skills in the workplace. And so if we look specifically here, this is knowledge of physics or astronomy. There are quite a large number of students that have entered the workforce that are reporting using this daily or weekly, but we've essentially fine-tuned the different qualities. And we see a similar trend for students who are working in computer science. So if you look on the right in the orange, the vast majority of students report that the skills they use almost daily include working on a team, solving technical problems, and as well also programming, as well as design and development, and some amount of simulation or advanced math. So these are skills that we in our program are working to bake into our curriculum so that we're able to train students for these skills that have been identified as being useful in the workplace. And when we talk about how we're preparing our undergraduate students, we do this a number of ways. So we prepare them both through our curriculum. So our coursework includes a sort of core of physics coursework, as well as electives the students choose. Many of our students also have extracurricular or metacurricular activities. They belong to clubs or they do research, and they have other experiential learning opportunities that they can leverage to build professional skills. So when we kind of discuss this at the departmental level, we often talk about, well, what are the overarching learning goals for our program? So any student who graduates with an undergraduate degree in physics from the Department of Physics, whether it's a Bachelor of Science or a Bachelor of Arts, these are the sort of learning objectives that they should be able to demonstrate by the time they graduate. And we essentially structure building our curriculum around these goals. And so first and foremost is, of course, the essential science and math skills. So the students are pursuing a degree in physics. We want them to develop subject expertise in physics, but then also in math, because it is a natural language that we use a fair amount in physics. And so CMU physics students, really, we want to build them up to be complex problem solvers so that they can tackle a wide range of problems using a number of techniques, and they can develop skills and knowledge that make them very versatile in this way. And so in terms of goals, apologies, one of the first things that we work in our classes is to develop a recognition of physical laws that are relevant to the problem. And this makes obvious sense, for example, in a classical mechanics class, but it also makes sense in a workplace environment where a student can hear about a problem or a situation or a product that's being developed, and they can recognize fundamental principles that relate to that goal or the problem that they're trying to address. And so this is something that gets practiced in our coursework and in our lab work and in our other activities. They then work to apply those laws to the problem. So it's not just a theoretical framework that we recognize, we also teach them to apply various principles. And then they address it using both mathematical and computational techniques. So our students are fairly well-rounded in their training, that they're getting both the conceptual framework, but also the mathematical and computational tools required to solve problems. Very often the most interesting problems cannot be solved analytically on the back of an envelope. So we ensure that our students have the tools to solve problems that sometimes are a little bit messy, because those are often the most interesting ones. And in order to do this, we make sure that they're using sort of all three legs of the stool of physics: experimental, computational, and theoretical methods and techniques. And it's not enough to be able to do a calculation or design an experiment. We also want to make sure that they're examining their findings. So we emphasize evaluation of findings, whether that is an analytic derivation or a data set collected in a lab. Assessment and evaluation of solutions and of findings is a key component of our curriculum. And so any student that comes through our program has this skill set that has been developed through the lens of physics classes and physics labs, but which can be applied much more broadly. Now, we recognize that our students don't operate in a vacuum, although that makes a much easier physics problem to solve. We do want to make sure that they're prepared for the environment that they're going to work in, not only for the types of problems they're going to work on. We saw on the AIP survey that our students leave and they do, for example, a large amount of teamwork, which requires communication and interpersonal skills. And so we also work to ensure that our students are developing professional skills that will aid them in the workplace. And so in terms of core professional skills throughout the curriculum, we emphasize self-assessment. So examining their own knowledge of an area and refining a plan to self-improve. And this essentially, the self-assessment and lifelong learning, these are skills that can take a student into any discipline. So the ability to read the literature, to search for resources, to recognize that you have a deficit and then address it, I think is part of what makes physics students so versatile. They're typically very curious, and they're very interested in growing in areas of interest to themselves. And we reinforce this throughout our curriculum by building sort of these independent learning skills. Now, we also find it important that they can communicate. We emphasize this along multiple axes. So oral presentations, that includes giving a talk or presenting a poster, a visual presentation of, for example, data. So making figures based on your data. This is a huge emphasis in many of our laboratory courses, or presenting diagrams, for example, in a report or on a poster to explain a complex principle or result. And we also have more formal written practice, for example, in writing lab reports or papers. And so these are essential skills no matter the area our students are going into, and they're one that we work to strengthen in our students before they graduate. Now, we have sort of other global professional skills that we emphasize as well. One of which is articulating their own skills. So not just assessing and having lifelong learning, but being able to explain where they are in terms of their learning as it relates to their engagement, and then relating that to larger issues, whether that is local, perhaps within an organization or within a community, and then also relating it to more global issues. And so the ability to take their skill set and apply it to other areas and to articulate how it relates, I think is very important. And then, of course, working on interdisciplinary teams. This comes very naturally into a lot of our coursework, in particular our laboratory work and our research experiences, where we encourage the students to work in groups. We facilitate and teach them how to be good collaborators, how to be good partners within a working environment. And this is something that we're really emphasizing as a professional skill based on what we've been seeing with the American Institute of Physics. Okay, so those are really lofty goals. How do we get there? So students have a lot to learn, both in terms of the content and then these overarching skills that we hope they'll be able to bring to you all upon graduation. We teach them through a number of ways. One is through their core curriculum. So every student takes a core set of physics classes if they are a physics major. They're rigorous. So the standards of excellence of Carnegie Mellon, I think, are fairly well known. This does not, physics department is not an exception to that. They have very rigorous coursework where they learn subject expertise. There's some flexibility that I'll touch on in a moment, but there is sort of a bare minimum standard that is itself quite extensive in terms of the training they receive. So there's a set core of classes that we know every student takes, which allows us to ensure that every student is able to hit certain outcomes. We do have flexible options for degree programming. Our students have a wide range of interests. Our faculty have a wide range of interests, and we want to reflect that in the options that our students pursue. Our department has expertise in a number of areas. We want students to be able to pursue curiosity in those areas, both in terms of one-off electives or in specialization or concentration via a degree track. And I'll talk a little bit more about that. And I want to point out that the vast majority of our students, I would say well over 95% of our undergraduate physics majors, conduct research on campus with faculty. This is an enormous percentage when you compare to other institutions. And this really is a formative experience for the students in terms of, although it's still in academia, working in a professional environment where they're not just solving problems for class, they're working on actual projects. And so I'm going to talk a little bit more about these three areas. So let's talk specifically about the physics core. So every student that comes through and gets an undergraduate degree in physics takes a subset of classes that is designed to give them the key framework they need to be a physicist. And so our advanced physics classes are designed to give that theoretical framework and also the analytic and quantitative expertise that we value. And so they take classes, for example, in electronics, in quantum physics, classical mechanics, electricity and magnetism, thermal physics, thermodynamics. And I can guarantee that every student that comes through our program has that key set of classes that allows us then to incorporate additional skills beyond just subject expertise into those core classes to ensure all of our students are meeting those standards. So for example, our lab classes, our students take multiple lab classes that are mandatory. They emphasize experimental design, data collection, data analysis, and data interpretation, as well as communication of those results. And so our students in particular, they start right off in their first year with a lab that has experimental design components. By their senior year, they're working on fairly extensive projects that are 3 or 4 weeks long in our senior modern physics lab and writing essentially a journal article level report on that. They are working with equipment that is not just plug and chug. So they have to troubleshoot, they need to analyze data and come up with ways to gauge the quality of the data. They compare to theory and to other measurements that have been made. And it's a fairly extensive laboratory experience. We have had students, I can think of 2 this past year, that got positions because they were able to talk about their upper level lab experience. And were hired into workplaces that emphasize skills that they learned in the lab. Communication skills are emphasized again across our curriculum. That could be oral presentations, written reports or papers. We have classes where our students conduct projects and then present posters to the community to tell people about their research or about their project. And what's interesting about this is part of this is also emphasizing communication to diverse groups. So a report that's written maybe for your professor or to be aimed at being a research journal article is very different than a poster presentation that's given to your peers. And so we focus at various levels, not just on communicating results and theories and findings, but also in terms of addressing who your audience is and communicating effectively to different audiences, which I think is a skill set that we absolutely work to refine over time. Now, in addition to that, we also emphasize computational skills. So all of our physics majors are required to take at minimum an introductory course in computer science, and that teaches them to program. Many of them go on to take advanced classes because they find them very useful or very interesting. But we also in physics apply that. So they're not writing programs just for program's sake. They're learning to take mathematical models that they've constructed using theoretical framework of physics, and then building models and building simulations of those models in their classes. So this happens as early as our introductory sequence. We have students working to conduct simulations of kinematic systems, for example, over time. These pop up in other areas of our core curriculum. For example, I know they're often used in our thermal physics classes and our classical mechanics class. And the students really are working on taking those computational skills and applying them to different problems in the context of a different sub-area of physics. And that, again, is a very translatable skill that they could take into various workplaces. Now, in addition to the core, the students do have a number of electives they're able to choose. And this is one area that we build flexibility into our programs, that students can fine tune or choose areas that are of interest to them. Our department has expertise in a number of different areas, and our elective classes reflect that. So we have a number of classes, for example, in advanced quantum mechanics or astrophysics and cosmology, biophysics, computational physics, general relativity, nanoscience, and nanotechnology, nuclear physics, optics, quantum computation and quantum information theory, solid state physics, and even more. So students are guaranteed to have sort of a set core. By choosing their electives, they're able to fine tune their program to meet their interests and the skills and the knowledge they're hoping to build individually. And so we have kind of a fairly wide distribution overall of skills that our students build over time. And so we have that core, but we allow students really to push in an area of interest to get expertise that they want. And in addition to choosing electives, we also have essentially degree concentrations that we call tracks, which are preset combinations of electives that allow students to essentially build expertise in an area that's been pre-identified. And we currently have 5 of these. So these are optional. Students do not need to do a track. But we have tracks in applied physics, in astrophysics, biological physics, chemical physics, and computational physics. And our 3 most popular are probably astrophysics, computational physics, and applied physics. So I want to touch a little bit on those. Let's go alphabetically. So in applied physics, our students are able to take a wide range of classes. This is one of the most flexible of all of the tracks. We encourage them to take as many lab-based classes as possible. And in this track, we often have students that take engineering classes. And we consider those applied physics. So a lot of the students on the applied physics track do have formal engineering training through some of their electives. It might not be enough to constitute a minor or an additional major, but they do have usually some amount of hands-on laboratory experience and potentially also some design experience through their engineering courses. Now, what's neat about that is you compare that then with the core physics curriculum. So you then have students who have fundamental design skills, who understand a bit about engineering and the engineering perspective and approach to solving problems, but they also have that theoretical framework and background of a physicist, which I think gives them a very sort of interesting combination of skills that they can apply to a wide range of problems. And we have a number of applied physics students who go on to do graduate studies in engineering or work in engineering firms. It pairs very well. A large number of our students on that track do consider an engineering studies minor, and our students that do additional degrees in engineering often pursue that track. Now, the next very popular track is astrophysics. On this track, our students take multiple advanced classes in astrophysics and cosmology. And they're also required to do research in astrophysics or cosmology. So they take a range of classes. The majority of these students are often intending to go into a graduate program, but we do have a number that have gone on with the astrophysics track into the workplace. So students, for example, who did internships at JPL or at NASA, we also have student graduates who have worked at the National Space Telescope Organization. So a variety of students from astrophysics that go on to do exciting things. And I want to emphasize also the computational physics track. This, I think, is one of our growing tracks that I think gets overlooked. So in this track, our students take not only introductory computer programming, they also take a minimum of 2 sort of additional computer science classes and imperative programming, as well as sort of the follow-up class. And they have very strong programming skills, but they also then take classes from us in computational physics. So they take 2 classes in computational physics. The second of which, our advanced class, has them working on a remote cluster, doing applications of machine learning or deep learning, And also they learn how to parallelize code to solve complicated programs. So not just the theoretical treatment of how to work, for example, with MPI or the multi-thread code, but they actually do it. So they actually do projects where they're learning and essentially applying these skill sets. And we have flexibility. We're trying to build more flexibility into this track to allow for students to take additional classes in machine learning or deep learning, et cetera. But students who come through this track are very strong in terms of their programming skills, but also in their ability to take complex problems and to break them into pieces to solve computationally using a number of techniques. And so I want to kind of emphasize that, because that's often when we see students, for example, that had jobs listed before that were things like software developer, software engineer, they often were on the computational physics track. We're seeing growing interest in data science, and we're working to incorporate elements of data science more also into our advanced physics class. And so I hope this time next year we'll have a 6th track. So we are talking about adding a track on quantum physics. So it's my hope that we'll have that to add to this collection soon. But essentially what these tracks are doing is they're identifying areas of specialization or expertise that a student has. And I think this is very helpful for students in terms of developing professional skills or skills that relate to a special area of physics. Now, the last axis I want to talk about in terms of our student preparation would be undergraduate research. I think undergraduate research is fairly common in a lot of STEM fields. At CMU, it's kind of notable that almost all of our undergraduate physics majors do some form of undergrad research. And there's sort of 2 main paths they take to this. They, of course, do it over summer, which I think is very typical across different organizations, as like an internship or a summer undergraduate research experience. They also take research for credit during the year. And so very often what we see is we see a student who'll work on a summer project and it will go very well. And they may then continue on that project during the year, but we assign them academic credit for that. So we recognize that as a valuable experience that we essentially assign academic credit for, which for a lot of our students makes it more accessible during the academic year. And we see students who, through their undergraduate research experiences, go on to do wonderful things. And I want to kind of emphasize that they're working on real research projects. So when we have students do research during the academic year, we're not sort of making up projects that just to keep them busy or to be busy work. The majority of them are really working on real research projects on the cutting edge of their field. We have faculty who are involved in collaborations, for example, with the Large Hadron Collider at CERN, which started up recently. We have faculty that are involved with analyzing data from the Webb Space Telescope, which has been in the news a lot recently. And we have undergraduate researchers who are working on projects related to those things. So they are really working at the cutting edge of their field with faculty who are experts, world-class experts in their areas of physics, and the students are working directly under them, gaining professional skills. And those skills that they build, this is one of the ways that students really can distinguish themselves outside their coursework. They develop a lot of professional skills essentially by being a professional researcher. We see students, for example, honing their communication skills. We have students who are authors on papers, who give conference presentations, but also in terms of the technical day-to-day skills. Our students are working, for example, the students that are in particle physics with some of the CERN collaborations, they are working with massive amounts of data. So big data techniques, they're learning skills for managing enormous data sets, for analyzing those data sets. There are a number of applications of artificial intelligence, machine learning, deep learning going on in the department. And students are learning that very often not through a class, although they might take a class. A lot of the time, the first exposure a student in our department has to these topics is through research, working on actual problems. And they come out with very strong skills in these areas. And I want to kind of emphasize that, again, this is This is for real. So this is not low stakes in class projects. They're working on fairly high stakes projects, really at the cutting edge of their field. And I just want to kind of wrap up, because I've talked a lot about what physicists can do and how we train them. And I think the emphasis I want to kind of end with is that physicists are natural, they're natural problem solvers. The training a physicist undergoes involves building, again, an analytical theoretical framework, and then coupling that with modeling skills, with mathematical skills, with computational skills that then can be aimed at any number of problems. And I want to emphasize in particular that CMU trained physicists have a lot to offer. They are some of the best in the country, and I know that I am biased because I teach and advise them, but I hope that you all consider hiring some CMU trained physicists or some physics undergrads in the near future. Thank you.
Thank you, Dr. Ryan. That was a really wonderful presentation. Our physicists are truly multifaceted individuals here from CMU, and it was great to hear about them and learn how they can be effective employees in almost any institution that there is. So thank you again. And this will conclude the Career Center's Talent Insider webinar. Thank you all.